And so there's the plan. Questions on any of that or concerns? Anything like that? Okay. All right. Is that everybody? Anybody else need a sheet? All right. So let's look at some example problems. So we'll just do the whole ordeal on all of these. Not every problem in the assignment or not every problem on the test, you'll have to do the whole analysis. So you might just have to do one piece of it, like what intervals are these increasing or decreasing, and you won't have to do concave up, concave down necessarily, but we'll just do all of it so we can get practice. So on all these, we got multiple pieces. We want to know the intervals where our function is increasing or decreasing. We want to know, bless you. We want to know all local minima and maxima. And we may have multiples, we may have none. And then we want to know intervals where f of x is concave up, concave down. And any inflection points. Remember, an inflection points where it changes from concave up to concave down, or concave down to concave up. That's what we're after on these. And again, you won't have to necessarily have to do all of this on every problem. Okay, we're just getting in the extra practice. So let's get a function here. So first thing we want to find the intervals where this function is increasing and the intervals where this function is decreasing. So let's look back and to get a little refresher here. We want to know increasing or decreasing. We're going to find the derivative, and then where our derivative is positive, that's where it's increasing. Where our derivative is negative, that's where it's decreasing. Okay. So first thing we got to do is find the derivative. This one's not too bad. We can do it all with power rule, so try to get the cobwebs out, get the rest off, whatever you want. Thinking about what's our derivative going to be on this one. Yeah, 3x squared. And then what? Minus 6x. Yep. Minus 9. And then the derivative of the 4 part is 0, so you don't have to write that down. I'll write down plus 0. So what we're after, we want to know when this thing will have a positive sign, one it'll have a negative sign. You want to know all those intervals. So our strategy we use is to find where it's going to be 0, and then we can pick a test point in all the pieces of the number line that we make chopping it up at those zeros. Because we know it can only change if it goes through 0. So we just can find where it's going to be 0 at first. So if we want to know where this derivative equals 0, we're going to go back to algebra a little bit. What can we do? Yeah, we can try to factor. If you really don't like that, you can use quadratic formula. There's really nothing wrong with that either. But here we take it and set it equal to 0 and solve. And so if we're going the factoring route, one thing we can do, we can factor out a common factor of 3. I'm going to make it a little bit easier. And then if you don't see that, you can still get there. Makes it a little easier to see how to factor the rest, though. We've got a trinomial. So we need factors of -3. That will add together and give us -2. Yep. -3 and +1. That's right. Don't have too many we have to check. Factors of 3 are just 1 and 3. And then we need -2 in the middle, so we'll go in -3. Okay. Here we can take each factor and set it equal to 0. If you just have a constant term, it ends up going away. Depending on how you think about it, you can say we're going to divide both sides by 3. That's one way of thinking about it. So if we divide this side by 3, the 3's will cancel, and 0 divided by 3 is just 0. So the 3 just goes away. Or sometimes you could say, well, I can do 3 equals 0, but that's not true, so just throw that away. Either way you want to think about it. So no solution from 3 equals 0, and then get x equals 3 equals -1. Okay. So those are the values where our derivative equals 0. Okay. And then what else should we be concerned about? There's actually one other situation we need to remember. Do you remember what it was? When our derivative equals 0 or our derivative has something else weird going on. Or does not exist, yeah. So if we have any x value where our derivative does not exist, we would need to include that on our list and as part of our critical numbers. And that's what we call our critical numbers, where the derivative is 0 or the derivative does not exist. This one, our derivative is just a nice smooth polynomial. It's not undefined anywhere, so we don't have to worry about that. So these are critical numbers. So we can use those to divide our number line up. So we got x equals -1, and then x equals 3. And we just want to check the sign of our whole derivative. So we need a test value in the left piece, a test value in the middle piece, a test value in the right piece, and then we can check the sign for each one of those. Okay. So I'll copy down our factor derivative again here. So it's 3 times x minus 3 x plus 1. You can use the unfactored version if you want to use it too. It's just sometimes a little quicker to use the factors when you're just checking for a sign. Okay. So let's see. We need a test value smaller than -1, so what do you want to use? Okay, so we can use -2. Let's do a different color here. So we'll use -2. So if I'm finding f prime of -2, I really don't care what the number is, I just care what the sign is. So 3 is going to be positive, always. Okay. And then -2 minus 3 is going to be negative, not -2 minus 3. So we have plus, minus, and then -2 plus 1 would be negative. So we have a positive times the negative times the negative. We get a positive. So on this portion of our number line, our derivative is positive. Do the same thing 2 more times. We just have to pick different test values. So what's a nice easy one in the middle piece? Yeah, I think 0 is good. Okay, so if we want to know about f prime of 0, 3 is going to be positive. 0 minus 3 will be negative. 0 plus 1 will be positive. So the whole thing is going to be negative. On this portion, our derivative is negative. We need to do one more. So we need something bigger than 3. What do you want to use? 4? All right, sounds good. So 3 is positive, and then 4 minus 3 is positive, and 4 plus 1 is positive. So this thing will be positive on that portion. Okay. So for, did I label them ABC? ABC, yeah. So for part A, we are increasing on what intervals? Yeah, negative infinity to -1. And then what was the other one? 3 to infinity. So we're just writing down those portions of our number line, and then we're decreasing where? Between -1 and 3. Those are answers for part A. Okay. Part B, screen's jumping. We want to know any local minima or any local maxima we may have. Since we've just done this thing with the number line, we can use the first derivative test. Okay. Remember, the first derivative test says that our minima or maxima have to occur where we have a sign change of the derivative, and then we just have to remember which type's which. Okay. We could do the second derivative test if we wanted to, but since we've already got all this, this is just a little extra work to do the second derivative, and then the second derivative can also come up inconclusive. So usually, unless you are already taking the second derivative for some reason, then the first derivative test is the winner. Okay. So we've got 2 sign changes. We got a sign change at -1. Our sign goes from positive to negative. So that's going to be a local extrema, but which kind is it? Is it a minimum or a maximum? So think about what that's telling us. This is charting the sign of our derivative. So that's saying our derivative has positive slope, and then it changes to negative slope. So that's a hilltop, so that's a local maximum. Okay. So we have a local maximum x equals -1. Okay. And then our sign change at 3 goes from negative slope to positive slope. That's a valley. That one's going to be a local minimum. Local minimum. Okay. And it's possible we could have these critical numbers and the sign doesn't change at all. Then we would not have either one. Or we could only have one sign change and we could only have one of these. Or we could have multiples and have more than one local max, more than one local min. All those are possible. Question on that one? Okay. And part C, we want to know where our function is concave up, concave down, and we want to know where any inflection points are if we have any. So part C, it's almost like the same routine, but we take the second derivative. So we take the derivative of f prime. So we need the derivative of 3x squared minus 6x minus 9. So what's that going to give us for the second derivative? 6x minus 6, that's right. So we're just taking the derivative of 3x squared, so 3x squared part's 6x, and then derivative of minus 6x is minus 6. So our second derivative x minus 6. Now we're going to do the same thing. We want to find out where our second derivative could be 0. This is linear, so that one's not too hard. X equals 1. And there's nowhere where it would be undefined or nowhere where our second derivative would not exist. So don't worry about that. And then on our number line, we're just cutting it into two pieces. Now we just got x equals 1, and we just need to pick a test value on each side. So something on the left, what value do you want to use? That's a good choice. We'll try 0, so again, we just care about the sign. So if we plug in 0, we'll get negative 6. So we're going to be negative. And we need to pick something bigger than 1. 2 is a good choice. If we want to plug that in, 6 times 2 is 12, minus 6 is positive. There's our sign chart. We want the intervals where we're concave up, concave down, and any inflection points. We are concave up wherever we have a positive second derivative. So what's our interval there? Starts at 1, goes to infinity. For concave down, wherever our second derivative has a negative sign. So concave down from negative infinity to 1. And then what point do we switch? X equals 1. So we have an inflection point. To x equal 1. I don't remember if WebAssign makes you actually put it in point form, or if it'll just let you give the x coordinate. But if we want to find the y value at our inflection point, how can we do that? Yeah, go back to the original function and just plug in 1 for x. So we'll make a little note here, if needed. So going back to our original function, so that would be 1 cubed minus 3 times 1 squared minus 9 times 1 plus 4. So let's see, that's 1 minus 3, negative 2, minus 9 is negative 11, plus 4, negative 7. So the actual point would be 1, negative 7. If I did all that right. And we could do the same thing for the local, for the local max and local min. If you actually needed it in XY form instead of just the X, you just plug those in. Question on that one? A lot going on in one problem. And again, you won't always have to do all this on every little piece, every little problem. Okay. Let's do another one. This one's 4-1. We did absolute max and min, and then 4-2 is the mean value theorem and Rolle's theorem, and then this is 4-3. And then we just got one more section. Yeah. Or is it 4-3 or 4-4? What I put on here? No, and I put 3. Yeah, it was 4. I just did them inverted. Hang on. So this is 4, 3 or 4. Hang on. I don't know. I'm all confused. I've been on spring break too. Yeah. So this is 4-3, and then 4-4 is L'Hopital's rule, I believe. What we'll do Wednesday. So. So 4-1's absolute max and min, 4-2's mean value and Rolle's theorem, 4-3's increasing, decreasing, concave up, concave down, and then 4-4's something completely different. But not too hard. Yeah, Wednesday before 4. Yeah. All right. Finding all the same stuff, just different function. So how do I get started? Derivative, yeah. Want to do increasing, decreasing, so we need derivative. That's going to be 4x cubed minus 4x. We want to make our little sign chart, so we need to find the critical numbers. We need to know where our derivative would be 0 or where it would not exist. And it's a polynomial, so it's defined everywhere. So we just really are concerned with the places where it would be 0 on this one. So set it equal to 0 and solve. Okay. What can we do on that one? Got to use a little bit different algebra skills here. Yeah, we got a 4x in common. I like that idea. That'll leave us with x squared minus 1. Then what? A couple options. I'll take either option. Be careful, because we'll lose a factor if we do that. Because if we do 0 divided by 4x, then we'll get 0. So. Yeah, what say again? And then x squared minus 1. Okay, that's good. 4x equals 0. X squared minus 1 equals 0. Okay, the other route you could take is if you happen to realize this one will factor again, you can do that. This is the difference of two squares. So I'll give you x plus 1, x minus 1. We'll get the same thing here. Okay, we're just going about it a different way. So we can divide both sides of this first equation by 4. Just get x equals 0. Second one, to get x squared equals 1, we just need x. So square root of both sides. If we do that, what do we have to remember? Plus minus. Yeah. So if you forget the plus minus, you'll lose a factor, and you'll lose a solution. Okay. So there are critical numbers. Here's our. I'm going to do a color here. -1. I got it. Okay. So sadly, we've got 4 test points we have to do, but it's not all that bad. So I'll copy down our factor derivative again. And if you notice that you could factor that again, then it makes it even a little bit quicker because you don't have to square anything. You get the same thing anyway. So we need something smaller than -1. So I would probably go with -2. 4 times -2 will be a negative. -2 squared will be 4 minus 1, so that's positive. So we'll get a negative. Okay there. If we do -2 here, that's negative. And then that one, you get 4 minus 1. So positive. All right, go. All right, you just. I was just trying to. Yeah, that's cool. All right, you just had to look on your face. Didn't know. Okay. So then we need something between -1 and 0. -1/2. Okay. -0.5. You want to think about it that way? Okay, so sadly, if you don't want to do the brain work, use a calculator. That's okay. Okay, so a negative times 4 is going to be negative. -1/2 squared is 1/4 minus 1, so that'll be negative. So we'll end up with positive. And let's see. something between 0 and 1, so we'll go 1/2. Yeah. Okay, so positive times positive is positive, and then positive 1/2 squared is 1/4 minus 1, so that's negative again. Get a negative. And then something bigger than 1, 2, it will be symmetric with it, okay. So 4 times 2 is positive, and then 4 minus 1 is positive, so we are positive. And just because the ones we've done, it alternates, it doesn't always. It doesn't always alternate between sections. So do the test points. Don't just guess that it's going to alternate. Okay. All right, so part A, where are we increasing, where are we decreasing? So we are increasing wherever it's positive, so that's between -1 and 0, and 1 and infinity. And our function is decreasing, -infinity to -1, and 0 to 1. B part, what about local minima, local maxima? So we've got 1, 2, 3 sign changes. So we've got 3 relative extrema. We just got to identify which type they are. So going from negative to positive at x equals -1, what kind of thing going to be, a minimum or maximum? It's going to be a minimum, yeah. So we're going from negative slope to positive slope, so that's in the valley. So we have a, I said relative, I think local minimum at x equals -1. And then we've actually got another one where we'll go from negative to positive at 1. And local max, where we go from positive to negative at 0. We need concave up, concave down inflection points. So to figure all that stuff out, we need second derivative. For our second derivative, taking the derivative of f prime, what we're going to get? 12x squared minus 4. Second derivative. Of x squared minus 4. We want to know where that's 0. So it's not going to be real pretty, but we'll just do it this way. Add 4 to both sides. Divide both sides by 12, so 4 over 12, 1 over 3. And then what? Take square root, yeah, I'm getting a little ugly here. Take square root, so when we do that, we gotta remember plus minus square root of 1/3. If you wanted to rationalize that, you can, but you don't have to. Plus or minus square root of 3/3. Okay. What we really want, just for picking test values, we want to know a decimal approximation so we can make sure we pick numbers on each side. Right? So, yeah. So that's like about something like that. Okay. Then we can do our sign chart. And so we've got uglier numbers, but we can still work with them. And so here's minus square root of 1/3. Here's positive square root of 1/3. The only thing that's really any trickier is just we have to be a little more intentional about picking our test values. So we need something to the left of something smaller than negative 0.58. No, it's the wrong side. Got to go negative 0.59. Yeah. Yeah, that's all right. That's probably not what I would pick. Yeah, I'd probably go negative 1. Yeah, that's easy. Okay. So let's see, we've got 12x squared minus 4. There's our second derivative. So if we plug in negative 1, will be positive 1 when we square it. So then 12 minus 4, that's positive. Okay. Then we need something in between them. 0 is a good choice. You could pick any value in there though. So if we plug in 0, what we're going to get? Negative 4, so that's negative. So. And then I didn't write 0 down. And maybe like 1. And then we'll have 12 minus 4, so that's positive again. Again, it's not always just perfectly alternating like that. Okay. Don't assume it is. Okay. So part C, where we concave up, where we concave down. So we're concave up, what interval? Negative infinity to, yeah, ugly number. And then we're also concave up, square root of 1/3 to positive infinity. Yeah. And we're concave down, negative square root of 1/3, positive square root of 1/3, or negative root 3/3, positive root 3/3 if you want to rationalize. We got 2 sign changes. We go from up to down, down to up, so we have 2 inflection points. So inflection points. At x equal plus minus square root of 1/3. 2 inflection. And then if we needed to get the y values for those, then it's a little bit messier because we've got that ugly x value. We could do it. Get a little messier. Let's graph this one. See if it checks out. Well, if we did all that wrong, would you cry? Think about it. Yeah, I would think about it too. I would really cry since I messed it up. Nope, wrong function. X to the fourth minus 2x squared plus 3. Okay. So we said we were decreasing from negative infinity to negative 1. That looks good. And we are decreasing from 0 to 1. That looks good. We said we were increasing from negative 1 to 0. That's good. And increasing from 1 to infinity. That's good. We said we had relative minimum at negative 1, positive 1. And then a relative, or local, that's what our book calls it, local maximum at 0. I hope that's what we said. Is that what we said? All right, good. Yeah. And then concavity. A little bit harder to see exactly where we transition. So we said we're concave up. This part's easy to see, it's concave up, but where does it change over? Right, where's that inflection point at? Harder to see. Yeah, so we said it should be at negative square root of 1/3 or negative square root of 3/3. Or we said that was about negative 0.5, what was it, 8. So let me see if I can get us a point somewhere in there. Somewhere in that area. Well, went too far. Really touchy. Somewhere in there where our concavity changes. Okay, so really hard to see because this part looks so flat. And then we got one that's symmetric on the other side, right where we go from concave down to concave up. So for sure, inflection points can be the toughest one to just look at and pick out. Okay. Sometimes they're obvious, sometimes they're not. Was that we did good? Do one more. Maybe a little bit more interesting. Those were just two polynomials, so. I didn't give you too many in the assignment either. A lot of the assignment just ask like, I have to say a function is increasing if the sign of the derivative is say greater than 0 or less than 0. Know which one. Those kind of problems, and then there's just a few where you actually have to do all this. Rational function. This works with all of our functions, and just while you're learning it, try to be nice and give you most polynomials so you don't have to get too complicated with finding the derivative or have too complicated algebra trying to find the zeros. Same strategy. On f prime, we just have to work a little bit harder on this one. Okay. Anybody remember how to do quotient rule? Minus, yeah. Yep, bottom squared. Okay. And it's minus. Okay. All right. So, derivative of the top, 1, times the bottom, minus top, times the derivative of the bottom, so derivative of x squared plus 1, what's that going to be? 2x? Or x squared plus 1 squared. Not as bad as you may think it would be. Let's simplify a little bit. I'm still not going to multiply the bottom out because we don't have to. But this is when you actually, probably make your life easier by simplifying some. Okay. So let's go one more. We got like terms to combine. So we got negative x squared plus 1 over. Okay. There's our derivative. To find critical numbers, we need to be concerned about 2 types of values. We need to be concerned about where this thing equals 0 and where this thing would not exist, or where it would be undefined. Okay, so let's handle the undefined part first. So for there, we only have to think about the denominator. So what x value would make our denominator 0? It's a good thought, but if we plug in -1, we square it, turns into 1. 1 plus 1, get 2. So there's not a real number that makes this thing undefined. Because even, no matter what negative we put in, it makes it positive, and then we're just squaring a positive number. That works. Okay. So we don't have to worry about this thing not existing. Okay. And then the place where this thing equals 0, we don't have to think about the whole thing either, because the only way this rational thing can equal 0 is if the numerator is 0, right? 0 over something. Because we already said it can't be 0. Okay. So we'll have 0 over something non-zero. That would be 0. So we don't have to worry about the bottom part to figure out when it's going to be 0. We just worry about the numerator. When is that going to be 0? And so it's not as bad as it might seem initially. So all we need to know when negative x squared plus 1 equals 0. And because of the way our signs are, I'm going to add x squared to both sides. Okay. So then we'll take the square root of both sides, and x is take the square root of both sides. What do we get? Plus minus 1. Plus minus 1. Not really any worse after you think about it a little bit. So, oops, sorry. I don't know. Hang on. So, okay. There's our derivative. This is when it turns out nice that we one place. we only care about the sign. We don't actually care about the answer, so we don't have to think super hard. So maybe like -2. So if we do -2 squared, that's going to be 4. But we got the minus sign. So I have -4 plus 1. It's going to be negative on the top. And then the bottom, what's our sign going to be? Positive. Yeah, don't overthink it. Look, we're double squaring things. Okay? So if we put in, no matter what we put in here, we're going to get something positive. Plus 1, still going to be positive. Squared is still going to be positive. So the bottom's positive. Okay, so negative over a positive, that's negative. If we go with 0, then on the top, that's -0 squared. That's just 0 plus 1. That's positive. What's the bottom going to be? Positive. Good. Yeah, don't think about it too hard. It's positive. So that one's positive. We go one more. If we go +2. 2 squared is 4. But then we get -4 plus 1, so negative on the top, so negative. Negative over positive. Again, that comes out alternating. Don't trust it. It doesn't always alternate. So we are increasing where? -1 to 1. And we're decreasing. Yep, -infinity, -1, and where else? 1 to positive infinity. B part. So we got 2 sign changes. We got from negative to positive at -1, so that is a min or max? Min. So local min. X equals -1. And the other one will go from positive to negative, so local max. And x equals 1. Now the part's a little bit more annoying. Because to do concave up, concave down, inflection points, we need the second derivative. So what do we have? -x squared plus 1. Or okay. Slightly more annoying. We got to do the quotient rule again. If our signs were just a little bit different, we could get some cancellation, but they're not. So. Okay. What are we starting with? We've got, here's our f prime g minus fg prime. So derivative of the top, maybe 2x, times the bottom, minus the top, times the derivative of the bottom. And derivative of the bottom, what do we have to do? Chain rule, yeah. Sadly. over bottom squared yuck. Let's see what we can do to make our life easier here. Bottom we're not worried about, that's easy. Just trying to get that top simplified some. So I'm gonna FOIL out the square here. So that'll be x to the 4th plus 2x squared plus 1. Okay. Looks like we got one more full ahead of us. If you don't have one like this in homework, don't worry. Okay, so that's negative x to the 4th minus x squared plus x squared plus 1. These cancel. So let's see, I think we're about ready here. I knew it was going to be a little messier, but I didn't work all the way through it. Let's see, so plus 4x to the 5th minus 4x. And so that's 2x to the 5th minus 4x to the 3rd minus 6x. Anybody catch anything? Is that looking okay? Over that same denominator, over 6 plus 1 and 4. Okay. All right, that one's uglier than I anticipated on the bottom. It's never 0. Top. One solution's easy. What's one thing that makes the top 0? 0. And the rest, not so pretty because if we factor out that x, we get 4th degree. So you do quadratic formula with it in 4th degree equation too, but rewrite it as a quadratic, but I don't want to do all that. So, like I said, you don't have one that bad on my homework. Right, let's look at the graph and we'll see where we can tell where it's concave up, concave down. I'll be happy with that. We could do it, it's just not worth it today. looks like. So looking from here over to here, what do you think about the concavity? Do you think it's concave up or concave down, like from here to the left? It looks like maybe it's concave down, yeah. And then some weird number in here, we got an inflection point, and it goes back to concave up until we get to 0. And then it's concave down, and then probably if I scoot over a little bit, really hard to tell on this side, but probably somewhere in here we got another inflection point that goes back concave up. So. Let's see. So maybe it depends on what solutions we get out. I think it would go positive, negative. Yeah. So no. Negative, positive, negative, positive. I think it would go. If you want an easy one to try where concavity is not going to change, to do x cubed. All of it's the second derivative. So first derivative is 3x squared. Second derivative is 6x. That would be 0 at 0. But on the left side, well, no, it does change this one. I don't know what I was thinking. So yeah, never mind. Oh, it does change. Concave down, left, concave up. Okay. I'll find one if you want to see one. Okay, let me give test back. Let's see. We'll stop the misery here.